Very good morning all. Welcome back to ATAL Library Day 6, Session 1. It is my pleasure to introduce Dr. Ayappa Swamy, Associate Dean, Associate Professor in the Department of Electronics and Communication Engineering at Aditya University, Andhra Pradesh. He completed his PhD in Vellore Institute of Technology, Vellore, with a specialization in hearing aid signal processing. He is presently pursuing a postdoctoral research at Newcastle University, Singapore. Dr. Swamy obtained his M.Tech in Digital Systems and Signal Processing from Eton University, Visakhapatnam, and his B.Tech in Electronics and Communication Engineering from Jawaharlal Nehru Technological University, Kakinada. His areas of specialization include signal processing, image processing, and Internet of Things. He has 30 years of teaching experience and 1 year of industry experience. Dr. Swamy has authored 30 publications in reputed journals. He has successfully completed a major funded research project titled Frequency Modulated Hearing Aid for Elderly with Hearing Disability, sponsored by DST, with a project outlay of 56 lakh. In addition, he has completed 2 consultancy projects with a total worth of 3.2 lakhs. We are truly honored to have you with us today, sir. On behalf of organizing committee, I wholeheartedly welcome you, sir. Now I request you to take over the session. Over to you, sir.
Good morning, everyone. Thank you, madam. Thank you for your nice introduction. Today, I'm going to discuss about the various digital signal processing approaches to compensate hearing loss. In hearing aids, mainly coming to signal processing, there are mainly 2 things. First is enhancing the signal, speech signal, that is denoising and reducing noise, and improving the quality of the signal. And second one is compensation, compensating the hearing loss. Okay, that is one of the main part in digital signal processing. So we will cover both. These are the contents, table of contents. First introduction, I think from last 5 years, 5 days, from last 5 days you are hearing about how ear works. There is anatomy and physiology of ear and how the ear processes the signals, and what is hearing loss, and what are the types of hearing loss, how they will be compensated using different types of hearing aids, all those things. I'm also listening that lectures and I structured my contents based upon what other professors discussed. Maybe 90% will be repeated, but some basics maybe they may be repeated. Okay, like introduction to the hearing loss, or is a people not like that. Maximum 5 to 10 minutes, I will close all those things. And first one is introduction. Next, types of hearing loss and signal processing or speech enhancement using hearing. Then 2 things are there now. First one is speech enhancement. That basically performed using this artificial intelligence and machine learning techniques. And next, coming to part of the hearing aid, compensating the hearing loss. We need to amplify the signal, speech signal. To compensate hearing loss, we need to amplify the speech signal. For that purpose, we need to use some signal processing techniques. Okay, and they are uniform filter banks, non-uniform filter banks, control filter banks, and transform-based techniques, and all those things. And real-time implementation we implemented on hearing aid prototype. That also I am going to discuss, and future directions and influences. How many of you are from technical background? I think all of you are. Remind me. Technical means E&CE or engineering background. They know about signal processing, filter design. Everyone? All of you. Okay, there is some rapid fire round. There are 4 rounds. First round, each round I have some 3 questions. This is basic information about hearing aids. Three types. What are they? Very good. Conductive hearing loss, and sensory neural hearing loss, and mixed hearing loss. Next. What does an audiogram measures? What does an audiogram measures? I think you know about audiogram. Audiogram, what does it measures? The degree of hearing loss in decibels. Hearing thresholds in decibels. Okay, that is the audiogram. Next. Which test is being conducted to record this audiogram? Pure tone audiometry. PT. Okay. Evaluation of hearing aids, starting from 16th or 17th centuries, they are here trumpet designed. It's an acoustic mechanical system. There is nothing electronics or anything involved there. After that, in 1930s, they invented a vacuum tube based hearing aid, somewhat big size. After that, analog hearing aid, which comprises of analog elements, resistors, transistors, capacitors, inductors, okay, and special purpose devices. After that, digital hearing aids. Digital hearing aids typically works with digital signals and digital processors and microprocessors. And then now, so much of research work is going on, and some in market, some hearing aids are also available with AI-based hearing. Introduction, we know that there are three types of hearing loss. Sensory neural hearing loss is the most complex when compared to conductive hearing loss. Conductive hearing loss is due to some obstacle in the ear, or some fluid, or some infection in the ear canal. Okay, that's the reason. It will be reduced using medication or surgery, small surgeries. Okay, next, this sensory neural hearing loss is due to the inner ear. Okay, the processing, main signal processing which was there in the ear, that is cochlea. If there is any damage in the cochlea, then this sensory neural hearing loss occurs. So there is a need of signal processing algorithm which amplifies selective frequency sensitively. Okay, why? Because this is a cochlea. Okay, each dots, color dots are nothing but hair cells. Each hair cell is responsible for a certain frequency, certain band of frequency, very narrow band frequency. Okay, due to easing or continuously exposure to loud noise or due to some medications, some hair cells may get damaged or lose their sensitivity. Okay, when particular frequency of sound reaches that ear canal, cochlea, that particular hair cell responsible for that particular frequency of sound will vibrate. Okay, but due to that continuous vibrations due to aging, they may get damaged. So that particular frequency range may lose sensitivity. Okay, the person can't hear that particular sounds. Okay, remaining sounds, no problem. That particular frequency of sounds, he may have some problem. Okay, so for that purpose, we need to amplify the audio signals selectively, not uniformly. We need to amplify the signals selectively for certain band of frequency with certain gain. Okay, that we need to perform using this compensation. Okay, hearing loss compensation. Okay, that is measured using audiogram. There are 5 levels of hearing loss based upon the gains and dBs, based upon the hearing sensitivity of that cochlea. That is normal, that is from 10 to minus 10 to 20 dB, 20 to 40, mild, moderate, severe, and profound. With respect to frequency, we will measure that is nothing but audiogram. Okay, audiogram is a pure tone audiometry test conducted on a person sitting in a soundproof room where audiologist will give a different audio signals starting from 250 Hz to 8,000 or 8 kHz with different levels. Based upon the response, a person has to press some switch if he is able to listen that sound. If he is able to hear that sound, then a person have to press that switch. Okay, based upon his response, audiologist will record for what dB level the person is responding. That is nothing but audio. That is for both ears. Okay, circle and cross is for both ears. Okay, next. This is a typical hearing aid block diagram. There is a microphone, as this is a digital signal processing. We need to convert that into a digital signal. Microphone picks analog signal, and that should be converted into digital. After that, speech enhancement. That we will be discussing. Nowadays, most of the hearing aids using artificial intelligence and machine learning techniques to enhance the speech, and then digital filter bands to compensate this hearing loss based upon the audiogram values. Audiogram values are the inputs for this digital filters. Okay, based upon that input, it will separate into subbands and it will amplify certain frequencies with certain gains. And then after gain adjustment, that is given to digital to analog converter. Again, we need to listen that analog signal. Okay, coming to speech enhancement. Nowadays in hearing aids, most of the speech enhancement is done using artificial intelligence. Previously, you use traditional signal processing algorithms like adaptive filters, Wiener filters, or beamforming, or multiple array signals. Multiple array multi-array microphone signals techniques. Okay, all those things are used to reduce the noise and enhance the speech signal quality. Nowadays, we are using industries are using artificial intelligence and machine learning to enhance the signals. Mostly, these are the advantages of this AI. The context awareness processing. Context awareness processing means based upon the context of the speech. For suppose in a speech, if a person speaking some the sentence, let us say, due to some bike noise or due to some train noise, if a certain word is completely masked with some noise, then A will predict that word based upon context of the speech. Okay, it will generate a same sentence, a same word based upon the context, and it will produce that. It will produce that with same pitch, okay, and same intensity. That is the context awareness. This is possible only using artificial intelligence. And speech enhancement and noise detection, okay, and automatic environmental detection. There are 6 types of environments hearing aid detects. First one is pure speech, no noise. First one is no noise and no speech. And second one is pure speech, noisy speech, and mission noise, and air noise, and music. Okay, based upon that, it will adopt certain settings. Okay. Next, real-time personalization. A person will adjust their hearing performance using some applications, mobile applications. We have that hearing aid matched with a mobile app. Whenever he feels in comfort, whenever he feels some betterment is needed, he may adjust some parameters in the mobile app or using some switches. Okay, that can be automatically adjusted based upon his improvement inputs for past few days. Okay, that is real-time personalization. And all those things. Actually, enhances clarity, comfort. Comfort is very important. For hearing aid, comfort is very important. If you have older people in your house, they are suffering from hearing loss, they are not happy to use their hearing aids for more than half an hour or 1 hour. Why? Because they won't feel that much comfortable. Okay, unwantedly they are receiving some high amplitude signals, noise. The noise will also amplified. Due to that, they will get some ear pain or irritation. Okay, so comfort is very, very important. Okay, so listening experience is also very important. Okay, deep learning based noise reduction. These DNA techniques are most classical methods, most preferred when compared to classical methods to reduce the noise. Benefits are lower distortion, improved speech, intelligence, robust performance, all those things. And these are all the common architectures: LSTM, CNN, UNet, and transformers. And these are the 6 environments: quiet, only speech in noise environment, wind noise, machine noise, music. Okay, based upon the environment, the hearing aid automatically switches. Okay. Mobile apps, if you take inputs from mobile apps and volume adjustments and listening patterns. Okay, based upon that user inputs, artificial intelligence will learn automatically and adjust automatically. That is personalized, more personalized. DNM based noise reduction improves. Discuss now. It improves speech. Next, which AI approach supports user performance learning? User performance learning. Reinforcement learning. AI models for speech enhancement. LSTM, BNL, CNN. Next, coming to heart of the hearing aid, that is compensation, hearing loss compensation. To compensate hearing loss, we need to introduce a selective and sensitive amplification techniques based upon a frequency. Okay, so for that purpose, we want to use these digital filter banks. There are uniform digital filter banks, non-uniform digital filter banks, and reconfigurable filter banks. The digital filter banks are nothing but which separates the input signals to certain band of frequencies. Let us say audio signal is of range, let us say 0 to 8 kilohertz. 0 to 8 kilohertz. Okay, for suppose if you want to divide this into 8 bands, we will consider in uniform filter bank, we will consider for every 1 kilohertz, we consider it as a 1 subband. Okay, 0 to 1K, 1K to 2K, 3K and so on, 8, 1, 8, 8. Using filter banks, we will divide that into subbands. And each subband is subjected to some gain for amplification. That gain values are taken from this audiogram. Okay, and for that digital filter bank is nothing but set of bandpass filters. Set of bandpass filters designed to divide the input audio signals into numbers of bands. Okay, these are typical hearing aid using digital filter banks. There we have considered, in this example, we have considered a number of filters. Each filter is given to, each filter output is given to gain adjustment block, and the gain adjustment values, the gain values are extracted from the audio. These are the bandwidths. This is the frequency response of that filter bank. Next, non-uniform filter bank. We know that hearing or ear is a non-uniform device. Ear is a non-uniform device. Okay, it won't receive all frequencies uniformly. So we divided that bands using non-uniformly using non-uniform. Here you can see first 4 filters and last 4 filters having some certain 500 Hz bandwidth, middle 4 filters having 1000 Hz, 1 kHz bandwidth. Okay, it performs better when compared to uniform filter. This is how the structure is realized. Okay, using MATLAB we design that filter, and one structure is used to extract 2 filter coefficients. Okay, so such that we need 6 filters to perform this 12 band non-uniform. These are those examples. We implemented this non-uniform filter band for different cases of hearing losses. First one is audiogram for mild hearing loss at high frequencies. First case, mild hearing loss at high frequencies. This person having a hearing loss at 4 kHz with a dB of 35 dB. That is a mild hearing loss at high frequency. In this case, here it looks like non-uniform, but because this is octave frequencies, one frequency, next frequency is double of the previous frequencies. Generally, audiograms are recorded at octave frequency. So they are amplified. They are given to that 12 band non-uniform filter bank, and each filter bank output is subjected to some gain values. These gain values are taken from at 4 kHz. The amplitude, the amplification is high. 4 kHz, the amplification is high. We need to measure the performance. You need to consider some parameters. First one is matching error, second one is delay for hearing aids. To compensate a hearing loss, we need to consider 2 things. First one is matching error. Matching error means comparison between audiogram and frequency response of the hearing aid. This is the frequency response of the hearing aid. Second one. First one is audiogram. Okay, we need to plot both in single graph, and we need to find the difference between that. That is nothing but matching error curve. Okay, that solid line is nothing but audiogram, and the dashed line is nothing but frequency response of the hearing aid, and the dotted line is nothing but matching error. Difference between audiogram and hearing aid. We will consider maximum matching error as a parameter to compare the performance. Okay, what is the maximum value? Okay, that we consider for evaluating the process. Okay, and that the audio signal, entire audio signal, real-time audio signals we provided that how it is amplified. And second case, mild to moderate hearing loss near low frequencies. In this case also same. Total 7. We perform it for hundreds of, but I presented only 7 here, 7 techniques. The last one is modeling hearing loss, moderated hearing loss at high frequencies, and plus conductive hearing loss. this person having both conductive. This is a mixed hearing loss. Conductive and sensitive hearing. Conductive means all values are less than 40 dB. So that is the reason for conductive hearing loss. Some frequencies having more attenuation. So that is the reason for due to the sensory hearing loss. So mixed hearing loss. Next, reconfigured hearing loss. The main disadvantage of with uniform filter bank is, or non-uniform filter bank is, the structure is fixed. The structure is fixed. Okay, we need to use all the 12 subbands, even if you want or if you don't want. That is the main disadvantage of this uniform or non-uniform filter banks. Okay, for certain case where there is only high frequency hearing loss, where there is no need for filter banks at low frequency hearing loss. In certain cases also we need to use all the 12 filter banks. That is the main drawback of a fixed filter bank. To overcome this, introduce reconfigured filter bank. Reconfigured filter bank means structure of a filter bank can be adjusted using some parameter. Can change the structure without changing the structure. We can adjust the number of bands. Without changing the structure, we can adjust the number of bands based upon some parameter. That is nothing but reconfigured filter bank. Here is the structure of reconfigured filter bank. Here, it comprises of two stages. First one is masking stage, and second one is multi-pass band generation stage. In masking stage, what we are doing is we are dividing total 8 kilohertz into 3 regions. First one is low frequency region, second one is high frequency or mid frequency region, third one is high. First one, stage. Okay. This is low, this is high, this is mid frequency. Okay, let us say 0 to 3 by 8 and 3 by 8 to 6 by 8 kilohertz. 8 by 0 to 8 by 3 kilohertz, 2 into 8 by 3 kilohertz and 8 kilohertz. This is one band, low frequency, mid frequency region and high frequency region. Okay, we are dividing that entire range into 3 regions in first stage. In second stage, what we are doing is each frequency region is separated into subbands. Each frequency region is separated into subbands. Either it will be one subband, 2 subband, or 4 subband, based upon our requirement. Here we are using a multi-rate signal processing to divide that into 1 band or 2 bands or 3 bands. Okay, if the variation in gains is high in certain region, there we need to use more number of bands, 4 subbands. Okay, if the variation is almost flat, there is no changes in frequency, then in that case we need to go for 1 subband. If variations or if slope of the audiogram in that region is moderate, then we can use 2 subbands. Okay, based upon our requirement, we can adjust that. We can position of flat switches S1, S2 and S3. Based upon that, we can reconfigure that. Okay, this is advanced thing. Here, main disadvantage is the same resource is used for all the 3 regions. So time delay increased by 3 times. Okay, so second stage, same resource, same structure is meant to be used for all the 3 regions. That is the main disadvantage of this. To overcome this, we invented this parallel structure based design. With minimal increase in computational complexity, there is gradual reducing time consumption. Same structure we implemented for parallel waves. Okay, here in this case, in first two frequency regions are divided into four subbands. Second region is divided into single. There is no subband division. Okay, as it is, the region is considered. Okay, this is the matching color. Second case, again, first two regions are separated or divided into four subbands, and third region is divided into two subbands. Like that. So based upon our requirement, we can divide that into. Okay, it will reduce the computational complexity. For one hearing aid, we can use a single structure by adjusting this parameters S1, S2, and S3 switches. It will reduce the computational complexity. Next. Which filter banks provides adjustable subbands? Which filter bank provides adjustable subbands? We discussed the three types. One is uniform, non-uniform, deconfigurable. Deconfigurable provides adjustable subbands. Remaining two cases, the fixed subbands. Okay. Next. What is the typical latency? Okay, it's a general topic. Mainly, maximum latency allowed for hearing aid is 10 milliseconds. Now, even though it is reduced to 5 milliseconds, the maximum. More than that, the person feels something lagging. That is, there is no correlation between lip sync and what he hears. Okay, that correlation exists. So 10 milliseconds. Okay. What is MME? One parameter which to assess the performance of the hearing aid, that is maximum matching error. Minimum mean square error, that is different. That is for signal processing communication type. For hearing aids, maximum matching error. A matching between the difference between audiogram and maximum matching error. Next, transform based. Next one is transform based technique. Here the signal is transformed to frequency domain. From time domain until now we discussed time domain techniques. Now the signal is transformed to frequency domain using some frequency transformations. Maybe DCT, wavelets. We use DCT. Okay. The main advantage of this DCT is operations all in real. If you consider Fourier transform, we need to perform complex operations. Okay, Fourier transform is complex transform. Complex means not difficult. It's a complex J plus J omega, that complex. Okay, so DCT is real. That's why we consider this DCT, and transformation is computationally simple. Okay. Now that digital information is transformed to frequency domain using 16-point DCT, in frequency domain, gain values are adjusted. Okay, these gain values are taken from audiogram. These gain values get adjusted in frequency domain, and after that, adjust means that frequency domain signal is converted into time domain. Let us see. Time domain signal, speed signal, is converted into frequency domain spectrum. What are we using? DCT. Using DCT, converted them into a frequency domain. Okay. Now, in frequency domain, we are adjusting the frequency, adjusting the gain values. Based upon audiogram, Based upon the audiogram, gain values adjustment is performed in frequency domain. In frequency domain. Simply multiplying these coefficients, these little coefficients with the gain values, audiogram values. Okay. After that, using IDCT, inverse DCT, they are converted into time. This is nothing but amplified or compensated, hearing loss compensated time domain signal. Hearing loss compensated time domain signal. DCT means, what is the full form for DCT? Discrete cosine transform. We mainly use for image processing applications. Okay, these are the results. These are the results for different cases, and this is the comparison table. Here you can see direct design, that is without filter bank. Direct design, it has some 8 bands, maybe number of bands, and it has some around 6.3 matching error, 6.39 decibels matching error, and 4.3 is the delay. Okay, and non-uniform and reconfigurable filter bank. You can observe different techniques in reconfigurable filter banks. And minimum delay got it for this DC, 16-point DC, that is 3.4 dB. 3.4 dB is the minimum matching error. Minimum maximum matching error. Okay, minimum value of maximum matching error. Okay, and for first example, and delay is 0.45 seconds. We implemented this structure using some real-time processor. We got the delay of 0.46 milliseconds. Okay, and proposed reconfigurable filter bank is also implemented. This proposed reconfigurable parallel reconfigurable filter bank. We got 2.5 dB minimum maximum matching error and 7.4 milliseconds. 7.4 milliseconds. And based upon the case, it varies. Okay, if all the three regions are divided into 4 subbands, then you get 7.4 milliseconds delay. Okay, this is a comparison. This is for first 4 examples. In this case, again, maximum matching error is 1.87 for proposed 8-point DCT, and for proposed 16-point DCT, that is 3.4 is the maximum matching error. Sorry, milliseconds the time delay. 1.91 is the maximum matching error. This formulas how to calculate, typically how to calculate this delay. Okay, we know how to calculate the maximum matching error. Simply difference between audiogram and frequency response of the hearing aid. Whereas for delay, we need to compute based upon the computational complexity. Based upon the computational complexity. For non-uniform filter banks, how many filters banks are using? M is the number of filter banks. Here we are using 12 number of filter banks, but for each filter we are extracting 2 outputs. So there are total 6 filters. 6 filters are used to generate 12 subbands. 6 filters are used to generate 12 subbands. How means? One filter structure will generate 2 asymmetric subbands. Let us say this is low pass, and it will give high pass filter. Based upon the symmetric property. Using the symmetric property, you can design 2 filters using 2 subbands using 1 filter. For 1 filter. Okay? So 6. Now I consider 71 the order of the filter. 71 is the order of the filter, and 71 order minus 1 divided by sampling frequency. Sampling frequency, 2 times of sampling frequency. Okay, we can say that is 32,000. Okay, so 6.56 milliseconds. That is how we calculate the delay for uniform filter bank. So non-uniform filter bank, fixed filter bank. For recurrent filter bank, it comprises of 2 stages. First one is masking stage. Second one is multi-pass band generation stage. In masking stage, we are using only one filter structure. Okay, and K is the order of the filter structure divided by 2 into sampling frequency. It is around 2.37 milliseconds. In second stage, we are using this multi-rate signal processing. Okay, in second stage we are using multi-rate signal processing. For that purpose, we need to consider n divided by 2 into m. That is upsampling parameter. D is the downsampling parameter. How many upsamplings and downsamplings we are performing, divided by 2 into f. Okay. For this case, we got 3.18 milliseconds. Okay, total is 6.3 milliseconds duration for both states combined. Okay. This is from transformed base. How much time required to find transformation, and how much time required to find the coefficients multiplied with gain values. Total 3.4 milliseconds. Next is we implemented using high speed, low cost, low power processor, that is ESP32 rover B. For that, consider ESP32 live at V4.3 board. That is audio board. Okay, audio signal processing board. You can do any projects using this. Even IoT projects, signal processing, speech processing, any type of audio or speech domain. You can develop your own what we can say Alexa using this board. It has microphones, 2 microphones, and connectivity for the speakers. It has IoT interface and codec, intel codec, and so many things are there. Okay, you can build your own audio system using this, music system using this. You can also develop your own processing or artificial intelligence, machine learning type of applications also you can use. The main advantage of this is it's having advanced codec. ES8388 audio codec. It is very high speed. It supports up to 96 kilohertz sampling frequency. A microphone in this board is also requires up to 96 kilohertz audio frequency. That is the main advantage of this. It's only 1500 or 1600. This board can use this for your audio signal processing applications. Very Python, you can also use Arduino IDE for this to configure this, or Python you can develop. Okay, we developed all these proposed algorithms. We implemented all these proposed algorithms on this DSP processor, and we tested it in real time using MATLAB. From MATLAB, we given audio signals to board, and out we received or we what we can say imported that output to MATLAB, and similarly compared both how the gain adjustment is performed. You can see here, this is the input signal, this is the amplifier, real-time amplifier signal. Real-time amplifier signal. Okay, using that assembling module, we tested that real-time performance. implemented for all the techniques. Okay, this is the input ranging from minus 0.6 to 0.4 amplitude, and after amplification the amplified audio signal ranging from minus 10 to 5 amplitude. Okay, there is a comparison in frequency, input to output comparison in frequency. There you can observe that this is for first case. There you can observe there is a difference of around 40 dB at 4 kHz. This is implemented for the first case. This is at 4 kHz, we have 35 dB attenuation. Okay, 35 dB loss, hearing loss at 4 kHz. For this audiogram, okay, this is the result in frequency. Okay, you can observe that at 4 kHz, the difference, the amplification is around 35 dB. And this is for second case. All the this is used. Okay, last rapid fire round. Let us see which transform is used in the proposed frequency domain method. DC, discrete processing class. Very good. The proposed 16-point DCT method achieves approximately 3.4 milliseconds delay. What is the codec? Is there in the ES32? Right? What is the number? ES8300 codec. That is the most advanced codec. Codec is very important for audio applications. Codec means coding and decoding the audio signals. Okay, from microphone, it will record the audio signal, it will convert into digital, and after processing again it will convert into analog. Okay, codec is very important. At the end, the speed of the audio processor, the signal or signal depends on this codec. Summary: filter bank and reconfigurable filter banks and reconfigurable filter banks, and frequency domain approaches. So implemented all three domains. For compensation, till now there is no AI or ML model because continuous process. The signal for enhancement we have some models, but for compensation, hearing loss compensation, there is no AI model still. Okay, we need to use only the conventional filtering or transformation type of processing, conventional processing only we need to use. For enhancement of speech signal, we have multiple AI and ML techniques, and all hearing loss cases tested with different types of audiograms having different hearing loss cases. All the four techniques we tested, and we concluded that 16-point DCT is better. Okay, you can play with different transformations if you want. You can play with different transformations, and you can also, if you want, you can also include one more stage for parallel reconfigurable filter bank. If you want, you can also have one more stage to further divide it into further number of subbands to increase the matching error. Sorry, to reduce the matching error. To reduce the matching error, if you want, you can add one more stage, that is the filter direction, or if you want, you can also use some other transformation techniques, or you can develop your own transformation techniques. And okay, if you want, you can also reduce the computational complexity. parallel structure based is somewhat complex, computationally complex. If you want, you can develop your own filter bank or parallel structure or some other reconfigurable filter bank to reduce the computational complexity. Even one multiplier or one adder, if you are able to reduce, then it shows significant change in the data. Okay, that's about difference. Any notes? Any doubts, or if you want any technique to be elaborated in detail?
So in the sampling we see the calculation of total 32 kilos.
Yes, yes.
Actually, I've taken FS only 8 kilos.
8, that is 32 is sampling frequency is 16.
For that.
2 into 32, 2 into 16 is 32.
So taken 8 kilos for the calculation.
Here, 2 into sampling frequency.
Sampling frequency is 8 kilos.
Maximum frequency 8 kHz. 8 kHz is the maximum frequency. Sampling frequency should be at least 2 times of maximum frequency.
16, but here
2 into sampling frequency. The formula itself 2 into sampling frequency. Sampling frequency is 16, but 2 into sampling.
and order of the filter is based on the
We selected based upon previous papers and guidelines. Okay, if you further reduce the order, it affects on maximum maximum matching error. It affects on maximum matching error and quality of the output. And if further increase,
can take the different results based on different order of the filter.
yes, we can take. But we found this 71 is what you can say moderately being some balanced between delay and matching error.
So compared to all the results, it is very configurated filter banks is only better compared to the non-uniform and direct designs.
Yes, 16-point DCT is giving better. As it is transform based, there is some degradation in the quality of the output. Always you need to go for filter bank structure. Okay, in the filter bank structure, reconfigure parallel structure is giving good performance. For a case example 4, okay, based upon the audiogram, the number of subbands are changing. Okay, based upon the number of subbands also, the matching error and this is also changed. DCT, as we are converting into frequency domain, there is small degradation in the audio quality.
So suppose I want to use Wiener filter as an isostructural result in hearing aids. How it can be used based on data?
No, Wiener filter is different. That is conventional signal processing technique.
Yeah, suppose I want to estimate for the DNN base. How it can be used?
DNN.
We are calculating the Wiener filter coefficients.
Yes, ma'am. So to calculate DNN filter coefficient, you have to use DNN.
Yeah, how DNN approach can be done?
I think better to go with not depending on these traditional separate AI techniques are there for denoising. That is perfect. But we can't combine this traditional with AI. We can't use this AI methods to find the coefficients. That is not suggested.
Suppose if you are directly using DNN, then pre-processing should be done by making use of short-time Fourier transform.
Sorry.
Can it be applied for the DNN?
No, I don't know. Actually, my work is on this compensation. Just now I started working on this speech enhancement using AI. That just now I started that. Till now I worked on this compensation of field loops.
You can adjust the bands, that is subbands based on AI
that can be done, madam, but that is separate or not in the filter bank, in the hearing aid. That is done in the stage of pre-processing. That can be not incorporated in the hearing aid. Audiologists may use that.
Based on the input signal, we can, that is first we has to select the number of subtracts, accordingly it has to change the filter design.
Yeah.
Keeping the same structure.
Yeah. That can be done by the audiologist. But audiologists don't have that much knowledge on this. They are not technical people. So we can develop on like application based upon the input audiogram values. We generate directly generate the gain adjustment values. That application can develop. But not in the hearing aid. It won't process in the hearing aid. It will process before feeding the values to hearing aid.
The real data sets available free for the speech enhancement.
Yes, ma'am. They are available.
Which one are the data sets?
Actually, now I am doing some literature review, ma'am. I need to get it. I am doing a PDF in this speech enhancement using this AI started PDF now. Till now I am using only this conventional signal processing algorithms to compensate
For using for AI purpose for
yeah.